go and explore the whole space and basically say, hey, what kind of new drugs are we going to try out? Because when you have one drug prototype, you go through multiple phases of testing, some on animals, some on people, with huge risk. And maybe it just pan out, doesn't work, right? I mean, sometimes you get lucky and then you get some really brand new drugs coming out, but most of the time it doesn't work. And that is basically constraining the drug industry. Now, from corals to the drug industry, to all kinds of stuff that we're doing in the world, and not only on software engineering, what we see is data as a problem, computers a problem, and how to make intelligent decisions out of these data as a big problem. Now, we know that human intelligence, such as Dr. Fleming, is great, but we don't know how to scale it. And as a society, this is actually the barrier that stops us from going to the next level of human intelligence. Now, of course, we're like, well, AI is great. It can solve all those problems, right? But at the bottom of it, AI is a software engineering problem, right? We write code, some sort of code. I mean, there's nothing magic. All those AI things that you're running on the phone, in the cloud, is composed of code. And that's basically done by the software engineering approaches that we've been doing in so many years. So the question is, how is AI changing our software engineering? Right. So before I went to AI and software architecting and stuff like that, and also management, because it's boring, but it's necessary, I started doing computer vision. And I would like to basically use computer vision as one example of how we start thinking about philosophy that guides all those AI development. So one of the fundamental problems that also dates from the Cold War days, well, God bless, we are past the Cold War days, but it actually sparkled a lot of interesting ideas. So in Cold War days, it's all about military, right? You have satellite images across the world, and you want to basically find out what kind of crazy Russian planes are out there in those satellite images. So one of the fundamental problems done by DARPA and the Department of Defense is basically saying, here's an image, and you basically want to figure out if there's a target airplane, where in that image is that airplane? Or do they have airplanes? How many airplanes are there? So one of the basic idea is that, you know, whenever we look at images, we know that edges, shape, contour is the most fundamental feature. Like if you have a kid, 1-year-old, they started recognizing things with shapes, and shapes are basically represented by edges. So you can basically take the image, the target image, and also the satellite image. You convert it in very simple ideas to edge images, binary, black and white. The way you compute it is basically comparing adjacent pixels. One is white, one is black. You know that's an edge over there, right? So you have the original images, you go to edge images. The way we compute edges is manual. You basically write, if I look at the left and the right, if there are opposing colors above a threshold, it's an edge. Right, so you get edge images and you see both. And it's like, how do I actually compare or match these kind of things? Now, one simple way for you to do it is basically saying, I'm going to be sliding this guy across the whole image, and for every little edge dot, I'm going to be computing if there is a nearby edge around it, and I compute for each dot the close edge it has. And then if all the edges on the target image has a very close by edge in this source image, then you know there's a match. The match score is basically the distance between all those edge points, right? And then you can manually design the threshold and basically say, if the average distance is going to be under 5 pixels, then that's my airplane. The whole thing is basically been designed, right? We're like, well, this is how we do it. It worked a little bit. I mean, well, World War III didn't start, so you know that it doesn't work very well. Right, so then we were like, well, if it is all edges, then we can do something more smart. And the way we do it smart is, let's look at, like how the edges are distributed across the image. If there's like this direction or that direction and things. And actually, me who just arrived used to be a colleague with me, and also he has again. So we were basically colleagues back at Google doing quite a bunch of computer vision and stuff like that. This probably looks very familiar to you. Is you can basically collect the local statistics of edges, and you can basically say, this is going to be the representation of this image. Now, if we have a car, then if you squeeze your eyes a little bit, you can basically kind of see that there is a car-ish thing. Not really a car, but there's like wheel-ish stuff here that looks like a door, that looks like a trunk, and things like that, right? you can basically say, okay, so now I have a more smart feature that's also manually designed. And you're like, I might be able to get something out of it. Well, it kind of makes sense because now you have wheels and it's better than these crazy edges. At least you have some sort of more high-level semantic features that's still designed. That makes sense a little bit more easy to understand. Now, is it working well? This is the approach that until 2012 is the best feature that we can ever have. And way actually, in 2012, we worked together at Google using those kind of features to do object detection and stuff like that, right? Kind of works. Still manually designed, manual logic, kind of works. And we apply this to a bigger image, then prompts start to emerge. Well, it doesn't really look like an image, right? There's kind of buildings out there, and there's a little bit of edges everywhere. It's definitely not as high quality as we want for a feature to describe images, right? We're like, well, yeah, it's okay, but it's not the best. So then the problem is, we can find algorithms or logic to detect an image. We can do one layer of what we call later known as pooling to collect some statistics. There's no way for us to go beyond that and get more semantic features out of these kind of manual logic. And so basically that kind of was the major bottleneck for computer vision for so many years that it basically introduced a huge depression among grad students because we are plateauing in our performance in computer vision because we don't have a good feature. Now today it's pretty well known that Alex Krizhevsky in 2012 was like, hey, you know what? I don't really need to worry about all kinds of manual features. Maybe I can just let a computer design and to infer from a massive amount of data. So what he did was he basically took the basic operation that we use to even detect edges, which is called convolution, right? You look at the local appearance of the images and you derive some statistics out of that. It was like, I can basically do convolution and pooling, which is collecting statistics. So essentially this one is basically one level of convolution and one level of pooling. Pooling meaning that you collect the statistics in a small range of an image. So I can basically stack that multiple times. So I'm basically saying I have one convolution on top of another, on top of another, on top of another. And then at the very end, I get some sort of a low-dimensional representation going from a huge image to a couple thousand features, numerical numbers. And then I can basically do a simple old-school fully extent layers or multi-layer perceptions to classify whether something is a cat or not. Now, this involves about 60 million parameters. In the past, it wasn't really possible for us to do anything like that because I dare you write out 6 million numbers, just like I don't need them to be semantic. Just write out 60 million numbers in an editor or on a paper. It's impossible, right? So Alex basically said, we have a huge amount of data. Let's just get the computer figure it out. There's an approach called stochastic gradient descent that allows us to basically initialize all those parameters in a random fashion and basically say, let's feed some data in it. And now what you can do is each little step, you take a few images, pump it through the whole training algorithm. It tells you the direction or the scale that the parameters need to go towards. And then you go a little step towards that better direction, and then after multiple rounds, then it gets the best performance. Turns out that this worked pretty well. And of course, turns out that there is actually a biological justification of it. So if you look at the human brain, this is what we call, this is an area right after the retina. It's called LGN. And what it does is basically it has the retina information feeding from the bottom. And the neurons, as we discover, is actually forming a layered structure with the previous layer neurons feeding information to the next layer, to the next layer, to the next layer, and to the top layer. You can at least count 7 layers on top, like in LGN. And what LGN is doing is very simple still. It's kind of like approximately here, like in the middle of your head. And then it passes on this information back to the back of your brain, which we call visual cortex V1, which is further doing quite a lot of layered structures, and then it further propagates these information up to what we call V2, V4, and a bunch of other places to infer objects, motion, and all kinds of semantics. So that makes sense. The performance is pretty good. And for all those hard-coded features, those kind of like squishy edges that we just saw, we were plateauing at 26%. top 5 guess. What top 5 guess means is there is a data set called ImageNet, and you might be pretty familiar with that. You take 5 guesses, what kind of things is in this image, or cat, dogs, cars, or anything. And then as long as there's one thing that's correct, well, as long as one of your 5 guesses is right, it's classified as correct. So even with that, there's basically a fourth of the chance that you're wrong. Basically, it's like that bad. Now, that has been plateauing for a couple of years, and then when AlexNet came out in 2012, it was like, wow, I'm able to cut that by almost 40% and going down to 15% accuracy, error rate, sorry. And that's a big thing, because we were like, wow, that's really cool. What it basically, looking back in the days, what we discovered was that we're able to basically get rid of all those hard-coded logic and basically say, why don't we do something that's more smart? Let's design an architecture, well, mimics human brain or not, an architecture, and it's kind of like basically like taking some Lego blocks and try to build out a model. And let computers figure out the exact numbers in it. And this philosophy basically guided us over so many years. And we have AlexNet in 2012, we have ZFNet in 2013, we have Inception in 2014 with my great colleagues back there. And that was the first time where we, I think, exceeded human accuracy. And then we have further performance down there over the years. And today it's pretty awesome. We're much better than human on this front. What basically that involves is basically in the AI world, we see quite a lot of trend going from logic, manual logic, to adaptive models. We see the same thing in natural language processing, so actually speech. So in speech, in the past, we basically manually design features that represents those kind of sound waves. We call it MFCC features and things like that. Turns out to be pretty difficult and turns out to be very constrained, turns out to be constraining the performance of all those speech models a lot, right? And then basically, around 2009, actually speech was much earlier in adopting deep learning. It was like, hey, we don't need to deal with all those manual features. Why don't we just feed in the crazy raw sound signals, and then let a neural net, recurrent neural net in that case, to figure out the structures and things like that. Worked out really well. And that's basically what all those speech recognition systems are doing today. Pretty amazing results. If you do Google Hangout chat, when I was driving, I actually used that quite a lot. It was performance is always pretty good, and even better nowadays. So that's basically going from logic to adaptive models. Well, basically in the classical world, we basically write code, and there's no difference in AI. You write code as well, right? This is a very simple neural net model that basically goes from input to a bunch of convolutions to linear and stuff like that. Don't bother reading it. Now, the next step is basically go from code to runnable stuff, right? And in the conventional software engineering world, that is called compilation, right? We all have our compilers. In the past, if we look 15 years ago, the whole Silicon Valley here is sprayed with two things. One is people who are making chips, and one is people who are making C++ compilers or C compilers back then. In the AI world, things are kind of different because you can't really expect this to be immediately runnable, right? We all know today that there's yet another stage called training. So essentially, this only defines the scaffold of it. The real meat of AI computation is actually the training phase where it feeds in or it fits those exact numbers or parameters or quote-unquote model before we can actually deploy those contents. And one pretty typical example is ImageNet training. So for ImageNet training, what we often use in this academic kind of fashion is we have about 1.2 million images, forming the data set of about 1,000 classes, so each class has about 1,000 images or so. For a typical day that we do, for a typical model that we train today, what we use is probably 1 exaflop of compute. Compute meaning adding 2 float operations or multiplying 2 float numbers or things like that. I was actually at London giving a talk and I was doing a little bit of computation. So assuming that every person is able to carry out 1 compute per second, and if you can assemble the whole people living in London, everyone in London, stop their work and do the computations, it takes them about 4,000 years to train that model. Now it's a little bit easier in China because there are more people, but it's still a pretty hard task, right? We started by doing experiments like this. That one is actually a Berkeley computer that we use to train a bunch of CPU models. That one is a pretty cute annotation of what kind of things we do with these kind of boxes. It's kind of amazing that we basically went so far with crazy compute and stuff like that, but really what we are doing today is we start to go from hacky hardware that pave us the way. And by the way, actually Alex Krzyzewski did his AlexNet paper with 2 GPUs. That's about $1,000 or so. It's kind of amazing to think that, well, $1,000 is something that we can pretty much spend ourselves, but the human intelligence is great over there, right? Now, we passed that period, and with all those crazy computation needed, we're pretty much in the phase of using really large clusters and very sophisticated scientific computation environments for us to carry out those. And 2 important trends emerged over these days. One is accelerated computation hardware. So NVIDIA, well, if you look at the stock price, they did pretty great, right? NVIDIA starting from 2008 or 2009 started investing really deep in deep learning. And it turns out that all those deep learning computation patterns are stupid. If you think about the all those kind of crazy programming logic, that's like if statements, then statement, branching, and stuff like that. For deep learning, it's much simpler. When you want to carry out a convolution or simply image multiplication, what it involves is basically saying I have this 1,000 numbers in an array, and I want to add or multiply these 2 arrays of 1,000 numbers, reduce them to one number, right? Matrix multiplication is essentially 3 for loops of matrix float number multiplications and addition. So that's a huge opportunity for GPUs and simpler hardware that can get rid of all those prediction, branch prediction logic, and all crazy kind of scheduling and stuff like that. Basically say I want to blindly carry out a massive amount of float operation. And GPUs are particularly good for that, which actually enables us to get about at least 10x performance gain and still 2x every year and things like that. The other trend is basically that we are seeing, such as DeepFi, as Alex just mentioned, and we're seeing a crazy growth of specialized hardware coming in this field. Or you can actually design special ASICs and stuff like that for us to carry out things at an even cheaper phase, right? So hardware really becomes a really important part of the whole AI evolution. And what we are seeing is basically the classical way of software compilation to get the binary becomes a pretty important compute phase or training phase, utilizing the crazy amount of data that we're having, the crazy amount of computation resources that all those hardware vendors are providing, and making it much better than conventional software compilation, which only looks at code itself. So we mentioned that we're chewing through a huge amount of data, right? So we used to be having this big confusion or big question in the big data area, which is we have a huge amount of data, but are we storing gold or are we storing garbage? Because people often think, there's a huge data being generated, it costs a hell of a lot of money to store them, right? I mean, storage is not only hard disks, but a lot of maintenance jobs and stuff like that. So we kind of hope that data could become a gold mine, not a liability, because if you want to store all those data, but having no way for us to use them, it's just crazy to spend money on it. So of course then we are basically thinking about with the 2 axes, one is data and one is algorithms, who is at the bottleneck, right? Maybe our algorithm is stupid enough that with more data it cannot get anything better. Or maybe the representation power of our algorithm is so good that we can just blankly pump up data to get a much better performance. Now, researchers in Facebook actually had this question as well, so we did a pretty cute experiment by looking at how larger we can go in terms of computer vision. So there's a very easy way for us to collect data nowadays. If you go online, there's a crazy amount of images being shared every day, and a lot of them are coming with hashtags or text or other metadata for us to infer labels out of it. For example, for these images, some of the labels go really deep and clean. Instead of saying bird, which is where we start with ImageNet, then we can basically go to eastern meadowlark, which is one type of bird. Of course, there's also environmental information out there. For flowers, we can go to bird of paradise. I honestly don't know the name of this flower, but I bet it's right. And also willow tree and things like that. So basically saying, with this huge amount of internet data, can we actually get some more information out of it, even with the same set of model, right? Assuming that our assumption is right, that the algorithm representation power is great, then we can pump a huge amount of data and get better performance. Now, luckily, it turns out to be so. So, a brave grad student, Alice Khrushchev's, well, actually, no, not Andrei Karpathy, did in 2015, I think, manually annotate a bunch of images in ImageNet and estimated that maybe the human accuracy is about 5%. Andrei right now is the director of AI at Tesla, a pretty smart young person who also coined the term software 2.0. So the previous state-of-the-art trained on 1.2 million images is about 3.8% error rate. Already pretty good, exceeding human accuracy. But blindly, by going up from 1.2 million images to 3.5 billion images, we're actually able to slash about further 30% or 40% of the errors and reduce it down to 2.4, which basically means, back to our previous assumption, that the representation power of our modules is really great. And what we really need to do is basically to have high quality or large amount of data that allows us to train and unleash the power in these models. Again, in the very beginning, we start with human reasoning of all those edges, like crazy stuff like that, trying to map edge images onto large images, or trying to collect some local statistics. That is kind of like baby steps. Today, we basically use algorithm combined with a huge amount of data for us to do the inference of complex logic. And essentially, when we think about software engineering in the AI era, we find that these are kind of like a circle of using better algorithms on a huge amount of compute resources to chew through a huge amount of bigger and better data for us to basically achieve the best performance. Now, of course, this, if we think about it in a kind of philosophical way, this whole circle, as we are doing modeling, training, experimentations, and things like that, became data itself, right? So in the recent years, there's even more interesting work coming out using the experimentation data that we have and basically say, hey, can we automate this loop further? There's interesting works called AutoML and stuff like that, allowing us to use computers to carry out this loop and basically say, let's accelerate this further and further. It's pretty exciting direction. We'll probably not have time to cover it, but it's much worth looking into. All right, so what kind of things we need to do in these kind of era? Now, one thing that's particularly interesting is I assume that a bunch of us at least have run experiments or tried out experiments and basically did AI as a researcher, right? And how do we manage those experiments? Now, I was looking back in my Google folder, Google Docs folder, and found this. We basically use Excel tables, and we're like, you know what? I ran an experiment, I got some numbers, accuracy, of course. I have some hyperparameters that I can barely remember. So let me list out one line basically saying this is the number of training steps per class, this is like the hyperparameters and things like that, gets the performance and things like that. And then in the end, we're like, well, this is untraceable. Right? It's just effing hard for us to remember what kind of things we tried out. Now, surprisingly, this actually happens in a lot of researchers. We're basically chatting with a bunch of researchers in NIPS and play around with how do you manage experiments with we don't know, Excel tables or just notebooks, crazy stuff. And if you think about it, let me ask this question. When you write your code, how do you manage your code? You have version control, right? You have Git, you have SVN. For the really old days, you probably use CVS. Well, actually, SVN is as old as CVS. And you have Mercurial and a bunch of other things. You don't put your code in an Excel table, or you don't manually trace the version of the code. The version control takes care of that. For AI, it's kind of the same. If you think about the fact that software engineering has become not only code, but code plus compute plus modules plus data, then we need to have a better way for us to manage those kind of computation and those kind of development cycles, something that we don't really have today. If you think of it further, how do you test your code? How do you ensure that your code is correct? There's this constant, this classical definition about continuous integration, or CI, that uses that enables us in conventional software engineering to guarantee correctness, right? There's Jenkins, for example. There's like Travis CI, and there's all kinds of crazy CI systems that people build to basically make sure that whenever you make modifications to your code, they're all correct with correct logic. There's a lot of software engineering practices such as unit testing, system testing, integration testing, and regression testing for us to do all those. Now, in AI, then it seems to be not really there today, right? You want to run some experiments, and suddenly someone changed the code, someone changed the module, someone changed the data, and a week later it's like, I can't even reproduce my results. How do I do it? And that's one of the biggest questions that we are having in today's AI development cycles, because we're like, well, what do we do? All those kind of classical software engineering practices still apply here. And as we are running really fast in this AI field, we basically focused on one thing, which is research and new ideas. But what we found in a product environment, in a large-scale environment, is that all those kind of things start biting us back. We're like, we need to basically borrow the conventional wisdom of software engineering, of computer science and computer engineering, for us to basically ensure that the AI development and research is going on in a very stable and reproducible way, not just running some experiments, putting the results on an Excel table, and hope that a month later we'll be able to reproduce it. Most likely, you probably won't. All right, but in any way, it's a pretty exciting field. If you look at the citation number of the original eminence classification paper from Young LeCun in 1998, we really see a more slow kind of growth over there, right? Seems that 2017 has plateaued a little bit, but never mind about that. There's a huge amount of interest, and that's basically why we're pretty excited about the AI field. And I think, like if we think back at the choral stories, if we think back the medical stories, if we are able to do all these and build a stable AI ecosystem software stack that would allow everyone to use it, similar to the way you use your phones to take a picture, that will make the whole human society actually progress much better, right? Because we know that we are kind of being capped by our manual intelligence. If we have the AI artificial intelligence layer to help us break that barrier, break that ceiling, that would actually potentially give us quite a lot of innovations in all kinds of fields, whether it be biology or medical or computer science. And that's a pretty exciting field. All right, so this is kind of like the interesting part that I think, because I've been talking about frameworks for so many years, and I'm really eager to talk about something beyond it. But let's go back to frameworks. We know that over the last few years, we've burned through quite a lot of different frameworks and stuff like that, and then we at Facebook were thinking about what kind of things